All right, folks, we're going to look today at another multi-body system type problem when it comes to free body diagrams and solving for different things of forces. And so basically, as a quick reminder, we need to look at how we go about doing that. First of all, we do a free body diagram of our system, a sum of forces of our system from that free body diagram. And from that, we're going to find the acceleration of our system. Now, then we'll look at an individual part of the system and find the sum of forces for that part, utilizing the acceleration of our system to then find our answer that we're looking for. Now, the next type of multi-body system we're going to look at is the Atwood's machine. Now, the Atwood machine is a very simple type of machine. It's just a pulley with a rope suspended over it with two masses attached to either side of the rope. Now, the ropes, for our purposes, are massless, and the pulley is frictionless and massless as well. So, really, the ropes and the pulley play actually no role in the motion of these two masses. This is a simple Atwood's machine. Now, to understand it, we're basically going to treat those ropes and pulleys like, well, they're only there to redirect the forces that are acting on the masses. So the ropes and pulley don't play a role in our system. Now, the only forces acting on the system, or these two masses, are their weights. So what we're going to do now is treat these two masses as a system. So we're going to remove the ropes and the pulley, and we're going to attach the masses in the same location that the ropes were attached. Now you notice that the weights are now sideways or horizontal, and that's because, well, they were actually pulling against each other if you look at the original problem. One was pulling down and the other one was pulling down, but both of them were pulling against each other. So this brings us an interesting dilemma, because now we're going to have to decide which one's going to be positive and which one's going to be negative. Now we're dealing with a system. Now, I decided to stick with right is positive, therefore left is negative. It's a traditional way of looking at it. You could do it just the opposite way of saying that left is negative and right is positive. It's up to you. So I then went about making a sum of forces using this free body diagram. First of all, M2G minus M1G would be what the sum of forces would be. Now, that's acting on both masses, and therefore we have a system's acceleration as a result. So, that being said, I would move on to solve for that system's acceleration. And it's simply a matter of dividing these two forces by the combined mass to find the system's acceleration. Now what I'd like to do is I'd actually like to use this to find, well, the tension that's acting on mass 2. Now, in order to do that, I need to look at what's going on with mass 2, just that one part. So, I do a free body diagram of just that part. That part has a tension pulling up, and it has a weight pulling down, M2G. Now, with this free body diagram, I can then do the next step, which is a sum of forces. Now, here's the weird thing. Down is positive. Now, down is positive because we chose to make this arrow, which was M2G, positive in the system. It's very important to keep that plus and minus sign that we use the same. So if we said in our system that M2G was positive, then in our part it also has to be positive. So M2G is positive minus tension equals M2, just the mass of that one up part, times the acceleration of our system. And then what I'd do is I would use that to then find out what the tension is. So do some algebra and calculate what the tension is, which would be T equals M2G, or the weight of mass 2, minus the mass 2 times the system's acceleration. And we've already had that equation in the first part. So, that being said, that's how we utilize a system to part approach to solving a multi-body system. And that's the Atwood's machine.